Welcome to Study Loop.
This is the answer to Chapter 14, problem number 5 from the Smith Organic Chemistry textbook. And so this problem gives us 3 molecules and asks us to look at the indicated protons. And so I've indicated them with red arrows here. And to determine whether those protons are enantiotopic, diastereotopic, or neither. And so remember, a good way to do this is to think about replacing one of the protons with Z or X, just a generic not proton, and seeing if that would give you enantiomers or diastereomers or neither. And so for A, if we were to do that, we would get a pair of enantiomers. So this is it's not a okay. So the carbon to which those protons are attached is not a chiral carbon to begin with, but if we were to make this instead, so CH3, C, and then let's put a Z, and then the other H is still there, and then CH2, 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 CH3. And so if we were to do this, if we were to replace one of the protons with Z, clearly we would be making a chiral center. And so since there's no defined stereochemistry to begin with, we'd be making a pair of enantiomers. And so this is enantiotopic. Enantiotopic. Okay, and so part of the reason for this is because this is a CH2, and so right now the carbon has bonds to 2 hydrogens, and then to another chain. Well, not another chain, but to the rest of the chain. So CH2, 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 CH3, and then its 4th bond is to a methyl group. And so the reason I point that out is because when we then look at B, we don't have. So this carbon, the carbon that the protons in B are on that we're looking at, that carbon is not bound to a methyl group. That carbon is in the middle of this molecule, so there's a plane of symmetry through it. And so even if we were to change one of those to a Z, we would still have a CH3, CH2 to either side of that carbon. So that would look like this. So here's the carbon, there's our Z. Here's our H, but then over here is another CH2, CH3. And so even if we change one of these protons to a Z, we're not getting enantiomers or diastereomers here. And so B is going to be neither. Okay, and so keeping these rules in mind, we can compare A and C. So what we should notice about C is that oh, did I arrow the wrong carbon in C? Oh, okay. No, I didn't. Okay. So what we should notice at C is that there is already a stereocenter. And so this carbon is already a stereocenter. So it has 4 unique bonds. So if we were to redraw this molecule, we could draw it like this. So right, so we could redraw this like this. C. CH2, CH3. Okay, and so if we were to go ahead and change, for example, this hydrogen to a Z group, so let's make this our Z. So now, clearly, we're going to have diastereomers, and I forgot to put that there. Okay, And so clearly we'll have diastereomers, depending on which of the two protons we decide to change. We'll get our two diastereomers. And so since substituting one of those protons with a Z group makes diastereomers, these protons are said to be diastereotopic. So diastereotopic. Okay, and so that's unfortunately the best way to do this is just to actually draw out what the molecule would look like if you were to substitute one of the indicated protons for a Z group, or you could use an X group or R or really anything just to show that it's not a proton. And then see if you get enantiomers or diastereomers. And if you do, then those protons are enantiotopic or diastereotopic, as the case may be. And if you do not, then they're neither. And so that's the answer to chapter 14, problem number 5.